Good afternoon, everybody. My name is David Galvin. I'm the chair of the Department of Mathematics. I'm delighted to welcome you here to the first Math for Everyone event of this academic year. For those of you who have only been here for a small number of years, I have to say that this Math for Everyone series began in 2010, and it was a regular event run by the Mathematics Department. We would typically have 1 to 2 presentations from exciting external speakers per semester. Unfortunately, in spring of 2020, something happened, and these Math for Everyone talks stopped. But I'm incredibly delighted that we're finally getting back to starting them again. And I want to say thank you to Professor Libu Nicolescu, who has worked tirelessly to make sure that this series has started up again. So thank you, Libu. I'm delighted to welcome our speaker today, who is coming from Michigan State University. Professor Bruce Sagan has been a professor in the Department of Mathematics there for 37 years.
Something like that.
For a long time. He is an accomplished researcher in the area of algebraic combinatorics. He's published 120 plus papers. He's written a wonderful book on the symmetric group. He has also spoken widely on mathematical topics, and he's also very valued at Michigan State as a teacher. He has twice been honored with the J.R. Crane Teaching Excellence Award from the Mathematics Department of Michigan State. And today, I'm very pleased to welcome Bruce, who is going to tell us about binomial coefficients. Thank you very much.
Okay, well, thank you very much, David, for the lovely introduction. And also thank you very much, Libu, for the invitation. And thank you all for coming here. I hope you will enjoy this. And I want to make sure that this is really math for everyone. And so if at any point in the lecture you have a question about something I'm saying, don't be shy. Just shout out, and I will be happy to answer any and all questions. I'm happy to have this be an interactive experience. So let me give you an outline of what we're going to talk about. First of all, I'm not assuming you know what a binomial coefficient is. So I will tell you exactly what the binomial coefficients are. And then we're going to play with them a little bit and look at various properties. So in the second section, I'm going to ask, are there good ways to compute these things? Can we find out what they are easily? I'll give you 2 methods for doing that. Then in section 3, I'm going to see, do these binomial coefficients count any sort of nice mathematical objects? And we will see that, in fact, they do count some very nice things called lattice paths, which, of course, I will define. Then in the 4th section, I'm going to tell you why the binomial, first of all, I'll tell you what it means to be fractal, and then I'll tell you why the binomial coefficients are fractal. They have this very nice behavior, which is often found actually in physical objects, but here we have it in a pure mathematical object. And then in the last section, I want to talk about an analog of the binomial coefficients called Fibonomials, where we combine the binomial coefficients with the famous Fibonacci sequence. And I'll mention some of my own research work at that point. And then I'll just have a slide of references for those of you that might want to look more deeply into this subject. I should say that these slides are on my website. So you can always, at any time, you can surf over to my website and find them and enjoy them and any of the papers that are related to it. So to start off, what the heck are these things? Okay. So binomial comes from Latin. 2 roots, bi, which means 2, bisect, things like that, and nomen, which means name. So 2 names. Okay, that doesn't really tell us anything mathematically, perhaps. So in mathematics, a binomial is just a sum of 2 terms. Polynomial, which is a sum of 2 terms. And the simplest possible binomial, and the one which we're going to be using, because I like simplicity, is 1 plus x, right? it's got two parts. It's got the one part and it's got the x part. So that is a binomial. Okay, so far so good. Not rocket science yet. Excellent. Okay, so what is a coefficient? Well, in mathematics, the coefficients of a polynomial in x are just the constants which multiply the various powers. Let me give you an example of this that'll hopefully make this very clear. Let's look at this polynomial, 7 plus 5x plus 9x squared. So let me rewrite that to emphasize the coefficients. So, right, 7 is really 7 times x to the 0, right? Anything to the 0 is 1. The 5 is multiplying the x to the first. The 9 is multiplying the x squared. And so the coefficient of x to the 0 is the 7, right? The thing that's multiplying it. The coefficient of x to the first is the thing that's multiplying it, which is the 5. And then finally, the coefficient of x squared. Any guesses? I hope you're all thinking it's got to be the 9, right? Okay, so these are the coefficients. So now we want to combine them. We've got a binomial and we've got to get coefficients. And here's how we get the coefficients. We take that binomial and we raise it to various powers. And then we look, right, that's going to be some polynomial in x. And then we look at the coefficients you get when you do that. Okay, so those are the binomial coefficients. Again, let's do a bunch of examples. This should become clearer. Well, the simplest possible power perhaps is 1 plus x to the first, which of course is just 1 plus x. So this has coefficients 1 for the constant and then 1 for the x. So this particular polynomial has two binomial coefficients, 1 and 1. Not very interesting, but we have to start somewhere. Okay, let's up the ante a little bit. What happens if we square it? Well, that's of course 1 plus x times 1 plus x. And now you can use the distributive law. So that's 1 times that second 1 plus x times that second 1 plus x. And now I'm going to write up both of those products, and I'm going to do it in a way that aligns like powers of x. So the 1 times the 1 plus x gives me that 1 plus x on the top. And then if I multiply it by x, I get x plus x squared on the bottom, and I've lined it up those two x's so that it's easy to see that when we add, we get 1 plus 2x plus x squared, which you probably already knew, but just trying to do things really, really slowly to start. So what coefficients do we have now? Well, 1, 2, and 1. Okay? Do one more, just for the heck of it. What happens if I cube it? Well, in that case, we can write that as 1 plus x times 1 plus x squared. We distribute. And now we remember that we just calculated 1 plus x squared in that previous part of the example. So we can plug that in and align like powers, add, and we get 1 plus 3x plus 3x squared plus x cubed. And so now we've got coefficients 1, 3, 3, 1. Any questions about how these coefficients are coming about? Okay, well, we want to be systematic about this. So we'd like to put these in some sort of format. And here's the format I'm going to use. I'm going to use a triangle. And I'm going to put on the rows of the triangle the various powers. And I'm going to align them, the various powers of 1 plus x. And so that'll be at 1 plus x to the n will be in the nth row. And then I'm going to align them so that the various powers of x itself form diagonals. So it's going to look like this. So right at the top, we have 1 plus x to the 0. Anything to the 0 is 1. Then the next line is 1 plus x. There's the 1 plus 2x plus x squared, which we had before, the 1 plus 3x squared plus x cubed that we had before. And I just did the next line just to give us a little bit more information. And notice, right, the leftmost diagonal is the constants. The next diagonal is the powers of x, then the powers of x squared, et cetera, et cetera, et cetera. Everybody see, you're going to be seeing a lot of this triangle it's important that it's clear what it's doing. Okay. Now, because we've been so cautious about how we've displayed everything, we don't really need those powers of x in there anymore. I mean, we know which row corresponds to which power of 1 plus x, and we know how far in a row to go to get the power of, say, x to the 5th. So usually this triangle is displayed by just suppressing all the powers of x and keeping the coefficients, because that's what we really want to look at. This gives something called Pascal's triangle. So, so the top row is 1, the next row is the two coefficients 1, 1, and then the 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And you'll pardon me if I don't write it all out. That would probably take too much time. So, clear what Pascal's triangle is. Any questions about the Pascal triangle? This is a good place for questions because it's the end of the, so that's the basic introduction to these binomial coefficients. Any questions? Okay, well, obviously multiplying 1 plus x by itself a lot of times is going to be a pain. Is there a nicer way that we can compute these things? And as I said, I'm going to give you two nicer ways to compute them. So the first one is a recursive formula. There's a very nice recursive formula for these guys. And just to set up some notation, this n over k in parentheses, this is read n choose k. And what it refers to, the n refers to which power of 1 plus x you're doing. So 1 plus x to the n. The k on the bottom refers to which power of x in that expansion you're looking at. So you're looking, n choose k is for the coefficient of x to the k in the expansion of 1 plus x to the n. Again, an example will make all this clear, hopefully. So 1 plus x to the 4th expands this way. Just believe me on that. So what would 4 choose 2 be then? Well, as I said, the 4 means that I'm looking at 1 plus x to the 4th, and the 2 means that I'm looking at the coefficient of x squared, which in this case is 6, right? Okay. Usually some of my students, when they're shy about answering things, they just put up the requisite number of fingers. I accept those answers as well. Okay, everybody understand this notation. We're going to be using this a lot. Okay, so here's how you can compute these recursively. First of all, I'm going to give you the boundary cases. Those are the two sides of the triangle. That triangle we saw, those are all 1s. So down the left-hand side, you'll always get 1. Down the right-hand side, you'll always get 1. And now I just have to tell you how to compute the ones in the middle. And it's a very simple formula. If I want n choose k, I take n minus 1 choose k minus 1 and add it to n minus 1 choose k. Okay. And to see this in more geometric terms, that's just a restatement of what we just had. Think of this recursion in the triangle. What is this saying in the triangle? Well, n choose k, remember, is sitting in the nth row, k in from the left, right? Where are n minus 1 choose k minus 1 and n minus 1 choose k? They're in the n minus 1st row, so just above. And one of them is just to the left of n choose k, and one of them is just to the right of n choose k. So basically, as you go down the triangle, you add pairs of adjacent numbers, and that gives you the number in between the two in the row below. Let's try that. So here's the outer, I said that the two outer diagonals are all 1s. How do I get the next element? Well, I need to add the two 1s in that row, which is 1, 1 together. And that gives me the 2, right? That's the 2 from 1 plus x squared, the middle coefficient. How could I get the next row? Well, I do exactly the same thing. First, I add the left 1 and the 2. That gives me my 3. Now I add the 2 to the right 1. That gives me, again, 1, 3, 3, 1. Remember, those were coefficients we got before. And you get a similar thing, getting the 4, the 6, and the 4. And you can keep doing that. So this is certainly easier than computing all those powers, but there's a fly in the ointment. What's the fly? The fly is, if I want to compute n choose k, I've got to compute a whole bunch of other things in rows further up, right? That's the problem with recursive things. In order to get to this row, I've got to do a whole bunch of previous calculations. Is there a way to not have to do those? To just look at n choose k and spit out a formula for it without having to do any other previous computations? Of course, there is. And let me show you that now. So this is just what I said about the problems with the recursive way. To tell you this method, we need a famous mathematical object called a factorial. So n factorial is just the product of the first n positive integers. So it's 1 times 2 times 3 up through n. So for example, 4 factorial would just be 1 times 2 times 3 times 4, which of course is just 24. So, very lovely theorem. N choose k can be computed in terms of factorials. It's just n factorial, the top factorial, and on the bottom we have k factorial, and we also have this other factor of you subtract k from n, and you take that factorial. Okay, so let's see that in practice. Suppose we wanted to compute 4 choose 2 again. Well, this formula says that it's what? It's going to be 4 factorial over 2 factorial times 4 minus 2 factorial. So that's 4 factorial over 2 factorial times 2 factorial. And you write out the factorials, 1, 2, 3, 4 on the top, 1 times 2, and 1 times 2 on the bottom. And you get 24 over 4, which yet again is 6. So this is arguably much faster than trying to compute that by going down Pascal's triangle to the row for 1 to the 4th. Okay, so those are 2 nice ways to compute. There are others, but I think that's enough for this part of the talk. Any questions up to now? Okay, well, I work in, as David was saying, I work in what's called combinatorics. Combinatorics deals with counting discrete structures. And so for me, an obvious question is, do these binomial coefficients count anything? And they do. In fact, they count massive numbers of things. Let me just show you one thing that they count, which is of particular interest to me. So we're going to be using the Cartesian plane. I'll call it P. So, right, the usual plane that you use when you're graphing functions and so forth, x-axis, y-axis, and I've, 1, 2, 3 out on the x-axis and so forth on the y-axis. And I've only shown you the first quadrant because we're only going to be doing stuff in the first quadrant, it turns out. So integers, as many of you probably already know, are the counting numbers 0, 1, 2, 3, 4, et cetera, and they're negatives. We use z for that because the German word for integer is Zahl, which begins with a z. Okay, so those are the integers. And what we're going to be interested in is what's called the integer lattice. So these are all points in the plane such that both their x and y coordinates are integers. Okay, so I've drawn a bunch of those points here. So, right, the origin, 0, 0, that's an integer point. And all of the integer points on the x-axis are, right, 1, 0, 2, 0, 3, 0. And then the same thing going up the y-axis, you have 0, 1, 0, 2, et cetera, et cetera. So we're only concerned with the points with integer coordinates, okay? And as I mentioned, what we're going to be looking at are what are called lattice paths. So a lattice path, so take one of these integer points, x, y, and a lattice path to x, y looks like the following. Start at the origin, start at 0, 0, and then take unit steps either north or east until you reach the point in question, okay? That is a lattice path. So let me do give you a quick example. Let's look at all the possible lattice paths ending at the point 2, 2. What do those guys look like? Well, let's think about it. We could start off with some east steps, say. If we take 2 steps east, then we have to follow them by 2 steps north, right? I can't take 3 or more east steps because that would take me past y equal to 2, and there's no way to go back if we're only taking east and north steps. So this is the only way of doing it if there are 2 east steps to start with. Okay, well, what if we don't start with 2 east steps? What if we start with only 1 east step? Well, then there's 2 ways to complete. I can go either east, north, northeast, or I could alternate east, north, east, north. Are we done? No, of course not, right? We don't have to take any east steps to start with, right? Suppose we start with a north step. Well, if we start with a single north step, again, there's 2 ways, which are essentially the reflections of the 2 ways I showed you at the end of the first line. You could go northeast, east, north, or you could alternate northeast, northeast. And there's finally, right, you got to go 2 north and 2 east. So the total number of paths in this case is 6. Everybody see why we get 6 paths? Questions about this? Any questions? Okay, well, what does this have to do with binomial coefficients, you may be asking? So let me show you a little table. And in this table, what I'm going to do is I'm going to take each integer point and I'm going to label it with the number of paths to that integer point, okay? So here's the table. So for example, on the x-axis, you only see 1s, right? Because if I want to go from the origin to a point on the x-axis, I have to just take east steps. There's no other way to do it. So there's a unique way to get to any point on the x-axis. Similarly, there's a unique way to get to any point on the y-axis by only going north. And then the other things I've just filled in, that 6 there is replacing the point 2, 2, right? We saw already that there are 6 paths there. Have we seen that before somewhere recent? Yeah, I see somebody is doing their fingers in exactly. This is just a rotation of Pascal's triangle, right? This is Pascal's triangle rotated on its side. And this is a theorem, of course. So the number of lattice paths from the origin to the point xy is the binomial coefficient x plus y, choose x. And let's just see that as an example. Let's go back and compute the number of lattice points to 2, 2 using this formula. So by this formula, what would that be? That would be the binomial coefficient 2 plus 2, choose 2, which is 4, choose 2. And remember, we calculated 4, choose 2 on the previous slide using factorials. That was 6. It's the same 6 that we were calculating using the lattice paths beforehand. So this is the way that lattice paths come into the picture. Questions? Any questions? Okay, so fractal. Why are these things fractal? And what is fractal to start with? So very roughly speaking, a mathematical object is fractal if it displays the same object at many scales. And perhaps one of the most famous of these is what's called the Mandelbrot set, which I'm showing you a picture of here. So notice there's that heart in the center on its side. And then just to the left of the heart, there's a circle with little circles coming out of it. But notice that circle with many circles coming out of it, that's everywhere. For example, on the top of the heart, there's a smaller version of it. And on the bottom of the heart, there's a smaller version. In fact, there are smaller versions of it all around the heart. And in fact, if you take that circle to the left with a circle on top, the circle that's on top of that circle is a smaller version of itself. So this is what it means to be fractal. You're getting things repeated at smaller and smaller, in this case, smaller and smaller and smaller scales. And this is something which happens not just in mathematics, it actually happens if you look at the coastline of Norway, for example, and you do this same sort of analysis, you will see that it is fractal. the way that the indentations of the fjords coming out and everything, it displays fractal behavior. So this is something which we see a lot even in nature, amazingly enough. So what does this have to do with binomial coefficients? The following. So I'm going to look at Pascal's triangle modulo 2, or just, I'm going to say sometimes just mod 2. What does that mean? It means I take each element in Pascal, each integer in Pascal's triangle, and I replace it by its remainder on division by 2. So if it's an even number, if I divide an even number by 2, I get 0 as a remainder. If I divide an odd number by 2, I get 1 as a remainder. So I'm going to replace each even number by a 0 and each odd number by a 1. Okay, so let's do that. So that's what I was just saying. So here's, and I've got a little bit more of it here so you can really see what's going on. So this is the full Pascal triangle. And now I'm going to, when I make the substitutions, I'm going to color them in whatever that is, magenta, I think, that color. So what does the top element become? Yes, oh, good. It's still a 1, right? It's an odd number, it's a 1. Similarly, the next two ones become 1s. This 1 is still a 1, but the 2 now becomes a 0. Very good. And then if we got a 1, next row is all 1s, right? Because they're all odd. I think you've got the general gist. So let me just do the rest of the triangle. That's what it looks like. And okay, so this is Pascal's triangle mod 2. Now do the following thing. Consider the triangle in the first 2 rows and compare that with what you get in the next 2 rows. Okay, so here is the triangle in the first 2 rows, right? Just a triangle of 1s. Look at the next 2 rows. Do you notice anything? I hope you do. And I think somebody's pointing it out to their seatmate. We have that exact same triangle on the left and on the right, and in the center, we just have a 0. Okay? Well, that was so much fun. Let's do it again. Okay? Now look at the first 4 rows and compare what happens in the following 4 rows. Okay? Here's the first 4 rows, and look at the next 4 rows. What do we see? It's the same behavior, again, at a different scale, twice as large. We take that larger triangle, paste it to the left and the right, and paste a bunch of zeros in between. This always happens. This is the fractal nature of Pascal's triangle. So here's the general theory. If I take the first 2n rows of Pascal's, 2 to the n rows of Pascal's triangle, and I look at the next 2 to the n rows, so in total I've got 2 to the n plus 2 to the n, which is 2 to the n plus 1 rows. If I call that top triangle T, in the next 2 to the n rows, I see T to the left, T to the right, and everything in the middle is 0. And this is actually not too hard to prove using the recursion that I showed you way back in section 2. If you're of a mind, take 5 minutes afterwards, you should be able to easily prove this. Okay? Questions? Any questions? Okay, so what are these Fibonomials that I keep blabbering about? Well, as I said, they have to do with the Fibonacci numbers. So Fibonacci numbers, probably one of the most famous sequences in all of mathematics. So you've probably seen them before, but just to make sure, they're defined recursively. You start with F1, which is 1, and F2, which is also 1. And then to get the Fibonacci numbers after that, you just add them, add the two previous ones, okay? So let's make a little chart. So here's n and fn. By definition, the first two are 1. I add the two ones and I get, somebody got their hands. Yes, thank you. I saw the 2. Thank you very much. And then I get 2 plus 1, which is 3, and 2 plus 3, which is 5, and 8, and so forth and so on. I know mathematicians who have this for their password. Yeah, kind of funny. Anyway, we're nerds. What can I say? Okay, so clear what the Fibonacci numbers are. Okay, what does this got to do with binomial coefficients? Well, actually a lot. I'm now going to, at the risk of looking a little crazy, define a fibotorial. So not a factorial, but a fibotorial. What is a fibotorial? So this is not the nth Fibonacci number factorial. So that's why I don't have the factorial sign down in the usual place. I have it as an exponent. When I have it as an exponent like that, I mean, take the product, not of the first n integers, but of the first n Fibonacci numbers. So f sub 1 times f sub 2, et cetera, et cetera, et cetera, okay? So for example, f5 fibotorial would be f1 times f2 times f3 times f4 times f5, and then referring back to our triangle, it would be 1 times 1 times 2 times 3 times 5, so that's going to be 30. Clear what fibotorials do for a living. Okay, well, now I'm going to throw caution completely to the winds and define the Fibonomial numbers by just replacing every factorial you had before by the corresponding fibotorial. So n choose k with a little subscript f, Fibonomial, is the nth fibotorial over the product of the kth fibotorial times the n minus kth fibotorial. Okay, well, just to do a quick example, what's 5 choose through 3 fibotorial? Well, we'd have f5 fibotorial and then f3 fibotorial, and 5 minus 3 is 2, so f2 fibotorial. So now I just multiply out all those Fibonacci numbers, right? So on the top, I'll have 30. F1 times F2 times F3 gives you 1 times 1 times 2. And then F1 times F2 is 2. Sorry, 1. So you get 15. Now, it's not, and I repeat, not at all clear from this definition that this is even an integer. It is, but who is to say that fk fibotorial times fn minus k fibotorial divides evenly into fn fibotorial? That is not at all obvious from this definition, but it's true, and we'll see why in a little bit. So, obvious things to ask is, are there analogs of the various things we've seen for the binomials for this new fibotorial type gadget? And there are. Let me tell you about some of them. First of all, the boundary conditions are the same, right? So if you were to make a triangle of the Fibonomials, the two diagonals would still be 1. That's easy to see. And the recursion relation looks strangely like the binomial recursion, right? Remember, what was the binomial recursion? It was n choose k is n minus 1 choose k minus 1 plus n minus 1 choose k. Well, the same Fibonomials are there. What's the difference? The difference is that both of them are multiplied by a Fibonacci number, right? So this is just some strange massaging of the binomial recurrence. Okay, very good. Well, so now you could ask, this is interesting. Do these guys count anything? And it's surprisingly hard to find things that these count. They are not like the binomial coefficients, which have many, many different sets of objects that they count. There's there was a long search with a number of papers before my co-authors, Curtis Bennett, Juan Carrillo, and John Mahacek came up with what we think is, quote unquote, the right combinatorial interpretation. This interpretation is a very interesting blend of, okay, so for the Fibonacci numbers, there is a standard combinatorial interpretation that uses what are called tilings. So you have a strip of n squares, and then you tile them with either dominoes, which cover 2 squares, or monominos, which cover a single square. And if you look at the number of tilings, it's easy to show that that is always a Fibonacci number. What we were able to show is that by combining that combinatorial description with the lattice path description that I gave you earlier, one can come up with a combinatorial description for these people. You might also ask, are these fractal? And they are. This is joint work with my graduate student, Shi Chen. They are modulo 2, they are fractal. But the difference is that right before, the sizes of the triangles were always powers of 2. Now they're not powers of 2, they're 3 times powers of 2. And that's just because of the way things work out. And notice this, either the first or the second property makes it clear that these are integers, right? From the first property, you can get the fact that they are integers just by using induction. And of course, if they count as set, they've also got to be integers, because I don't know any sets that have 3.5 elements in them. Okay, so that finishes up that little thing. So I always like to end my talks with an unsolved problem. So I'm going to do that now. Let's look at the Fibonacci, just forget about fibotorials and Fibonomials and all of that. Just look at the ordinary Fibonacci sequence, but do it modulo 2. Okay? It's the same way we were doing for Pascal's triangle. So there's the Fibonacci numbers, and now I'm going to do it in mod 2. So remember, mod 2, replace every even integer with a 0, replace every odd integer with a 1. So we start off with 1, 1, 0, 1, 1, 0, 1, 1, 0. Does anybody see a pattern? Yeah. So modulo 2, the Fibonacci sequence just goes 1, 1, 0, 1, 1, 0, 1, 1, 0 on forever. Okay, and again, that's easy to prove by induction using the recurrence for the Fibonacci's. So we say that this sequence is periodic with period 3. So periodic means that it repeats. Period 3 means that's the smallest length of a repeating bit. Okay. It's very easy to prove, again, using pigeonhole principle, that for any positive integer m, if you look at the Fibonacci, so this is not just modulo 2. This is, you could have used 3, 5, 16, 2 billion. It doesn't matter. It is always periodic. The amazing thing is, nobody knows a general formula for what that period is. I mean, we just saw that it was 3 for 2. And, you know, for certain small numbers, people know what the period is. But there is no known way of predicting what it is in general. That's just a totally open problem. So if any of you have ideas of, I'm sorry, what?
Yeah, it's prime.
Not even for primes. Not even for primes. So yeah, if any of you have an idea of how to solve this, please talk to me so we can write a paper together and then get the Fields Medal or something like that. Anyway, it's intriguing that something this basic and elementary should still be open. So just to give you some references, first paper is stuff about these Fibonomial coefficients. The second one is the one that I talked to you about, where we give the combinatorial interpretation for them. The next one is the one about the fractalness. The fourth one is not the book that David mentioned, but my most recent book, which has a lot about Fibonacci numbers and other combinatorics in it. And the last one is about a vast, so you can generalize a lot of what we have been talking about to, rather than just using the Fibonacci sequence, using a general sequence of the form three-term recurrence, where the given term in the sequence is some constant A times the previous term plus some constant B times the one before it. And so that approach is what's taken in the last paper. And I think that's all I have to say. So thanks again for listening. So are there questions, any questions at the end? Go for it.
Can you at least say the period is no more than?
Yes, there are easy upper bounds. None of them are very good. And the other thing that makes this crazy is the thing isn't even monotonic. If A is less than B, it is not necessarily true that the period modulo A is smaller than the period modulo B. It just seems to bounce all over hell and creation.
Characteristic question for recordings.
Right.
You have to take a square root of 5.
Right.
If 5 is quadratic raised to 1, you could write down formulas in that case.
Yeah, I mean, you got an explicit formula for the nth Fibonacci number. That doesn't necessarily, well, I don't know. Maybe you could.
You have a combination of the two roots, and then you look at their periodicity, the group of.
Well, that'll give you a bound. That won't necessarily give you the actual period. That's the problem. Other questions? Yes. I say again. Oh, sure. Simple as possible. The reason that it's called N choose K is because of the fact that it is the number of ways of choosing a K element subset from an N element subset. So that's a very, very simple, and it's not hard to see why the lattice paths and these have to be the same thing. They also count other things. So, right, if I'm picking a set, I am always not allowed to have two things that are the same in the set, right? The set has got to have distinct elements. If you look at what are called multisets, which are collections of elements where you are allowing repetition, binomial coefficients also count those, which is, yeah, that is kind of mind-blowing, but it's true. It comes from something called combinatorial reciprocity. They count certain types of integer partitions. They're all over the place. Other questions? Yes, Misha. You mean not just the three? In general, it doesn't. They don't work. They don't. These you can define them, but they don't turn out to be integers. So we don't have any other large class. That's the largest class we know of where we're guaranteed to have integers out of there. Even when you do something simple, like look at the tribonomials, which are right, falls apart. Yeah, it's a little bit strange. But there's reasons for that. So these Luca polynomials, the ones that have just the two terms, there's a close relation between them and cyclotomic polynomials, and that's what drives it. What happens is that what you what you do is you end up factoring the top and the bottom in terms of cyclotomics. And then you see that all the cyclotomics in the bottom cancel into the cyclotomics in the top. And in general, that's just not going to happen. Other questions?
So let us thank Bruce again. And pizza will appear on these tables in the next couple of seconds if people will just help carry the boxes down from the atrium over there.
And if you have signed, there were those sign machines. Please return to the.
Claudia, oh my God. That's such a big thing. Oh, I'm going to have you been in touch with him?
I talk all the time.
Oh,
Yeah, I work with him and I talk all the time. Yes, yes, the factor is the problem in the afternoon. And I told him I was coming to your door. And he said, please, send all my best to you.
Now, if you win them.
I've been here actually for 20 years.
You like it here?
Very good.